A fly flies along y is equal to x to the third, such that the position of x at time t is given by 2t plus 1. Now when I say the position of x, I mean the x coordinate of the fly. And then comes a question about not about the displacement or the position, it's about the velocity. And it's not about the x component either, it's about the y component. So that's interesting. Well, let me start by saying that you want to find the velocity. So to reformulate this, the velocity of y, which should be a function of time, because I am presuming now that the velocity changes with respect to time. This is what we are trying to find. Okay, and what is given to us? There is a relation between x and y. Maybe I'll do like this. But this doesn't mean anything. It's not like formal notation for anything. I'm just saying there's a relation between x and y, and there's a relation between x and t. So what is the relation between y and t? This is food for thought. I'm trying to show how one might familiarize themselves with the concept that's involved with this type of question. So, there is also another pertinent question, which is, what does the velocity have to do with the displacement? What's the relation between the velocity and the displacement? So that's a good question. And the answer to that is that the derivative or the rate of change of displacement gives you the velocity. And I put this again between quotations because these are all ideas that I'm feeding to you right now. They're not anything that's formal, but we seem to be making some connections now, which is good. Okay, if velocity is the derivative of displacement, then this is probably so it's a derivative with respect to time, of course. When I say derivative of displacement, I mean with respect to time of the position of the y component of t. So that is good. Okay. So this is what I want to find. There's a relation between x and y. Okay. This is a lesson about derivatives, so maybe we should take the derivative. So if y is equal to x cubed, then the rate of change of y with respect to t is equal to 3x squared times the rate of change of dx with respect to time, dt. Okay, so that's even more progress. It seems that we're formalizing this idea that there's a relation between x and y. Okay, and finally, there's something that we still have not utilized in our construction, which is this x as a function of time. Well, here's the catch. Catch it. Should catch it. So I'll color this in green because if x of t is equal to 2t plus 1, then dx, d by dt of x of t, which is actually dx by dt, same thing, is going to be equal to the derivative of 2t plus 1. And this is just 2. Okay, so it seems like everything is coming together now, which is good. I'm happy. And it seems that taking the derivative of y and x with respect to time was a really good idea, because y is the y component of the fly, x is the x component of the fly, and they are both changing with respect to time. So in some sense, they are functions of time. So it's a good choice to make there. Okay, then dx by dt is 2. Then dy by dt, which is actually also d by dt of y, is going to be equal to 3 times 2 times x squared. So 6x squared. Now at time t is equal to 1, what is x? Because we don't know, we know y, but we don't, but we need to find something in x. And for this, actually in this case, if t is 1, then x of 1, x of t is equal to 1 is equal to 2 times 1 plus 1. So it's 3. We're getting really close to the solution. So finally I can write that dy by dt, which is a function of time, at 1, so at t is equal to 1, this is going to be 6 times, well, the value of x at t is equal to 1 is 3. And then you square that, because this is what we are doing here. We're replacing x for 3. 3 squared is 9, and 9 times 6 is 53, right? 54. Forgot my arithmetic. But then that is almost it, because you should not forget your units. You could say the velocity is 54 units per second, for example. Units are important. But this is how you proceed. So on a very basic level, these are the, I don't want to say intuitions, but intuitions that you should have about the problem, at least initially, upon reading it. And this is how you should proceed. You have some givens, which you need to utilize. If you're not utilizing your givens, then probably something is wrong. It is very rare to happen that too much info is given to you with regards to a certain problem. Usually all the info is relevant for the problem and is there to help you. And so if you're not using the fact that t is equal to 1, or if you're not using the relation between y and x, which allows you to establish a link between y and x by this equation, then you need to think of how you can work with that. And since we know this is about derivatives, then we take the derivative get lucky and we get the right solution.